This video is about a conflict in physics that dates back 100 years and still remains unresolved today. This video is in three parts. Firstly, I'll talk about the history of a conflict in physics which dates back to 1905 and 1935. Secondly, I'll summarize present-day research in this area. And finally, I'll talk a little bit about my approach to space-time foundations. Part 1. History of a conflict in physics. There is a conflict between two major theories of physics. Einstein's special relativity theory of space-time from 1905 and quantum mechanics, the theory of atoms, from the 1920s. Einstein called this conflict spooky action at a distance. This graphic is from the 2022 Nobel Prize for Physics. So-called entangled quantum particles, like electrons, behave as an integrated single unit, even if separated by great distances. This connection that ignores distance seems to contradict our expectations from Einstein's theory of relativity. So let's take a brief look at that theory first. Einstein's first theory of space and time is called special relativity. This combines 3 dimensions of space and 1 dimension of time into a single 4-dimensional space-time. In relativity, the speed of light is a fixed limit. A central idea, originally from Minkowski, is that 4D space-time is something like a fabric or a jelly. It can be bent by matter or even vibrate as gravitational waves. Consider the speed of light. As shown in the diagram, a beam of sunlight on its journey to Earth takes 8 minutes to travel the 148 million kilometers from the Sun. There is no possibility of sending a message any faster than this. Imagine that Alice wants to send Bob an urgent message. Relativity says that no messages, nor an influence of any kind, can travel between Alice and Bob faster than light, with no exceptions. Although quantum physics obeys this no messaging rule, it does find an exception. This is Einstein's spooky action, also known as quantum entanglement. There occurs an inexplicable coordination or correlation between Alice and Bob. So we have conflicting pictures. On the left, relativity expects everything to obey the speed of light limit. However, the picture on the right of quantum entanglement doesn't seem to belong in a space-time diagram at all. How are we even supposed to draw space and time axes? These issues were debated in the 1920s and 30s between Einstein, Bohr, and many others. At a purely technical level, quantum entanglement is very well understood. However, the philosophical and space-time implications remain unresolved. These debates culminated in the famous 1935 EPR paper named after the 3 authors, Einstein, Podolsky, and Rosen. Einstein's objection was that this spooky coordinated behavior, which somehow ignores all normal ideas of space, must indicate a failing of quantum theory. In fact, this strange behavior absolutely does happen, as we will see next. This is Einstein's most cited paper and has generated huge debate. The next major breakthrough came from John Bell in the 1960s, working at CERN in Switzerland. He came up with the Bell inequalities, which are equations allowing experimental resolution of philosophical arguments. We now refer to spooky action as Bell nonlocality or quantum nonlocality. John Clauser took note of Bell's results. In 2022, Aspey, Clauser, and Zeilinger received the Nobel Prize for performing experiments verifying that Bell nonlocality absolutely does occur as predicted by quantum theory. Notice, however, that these experiments merely confirm the problem. They simply deepen rather than resolve the philosophical mysteries. Here is an experiment that illustrates the problem. Two entangled particles are initially in contact. The particles then move far apart. On comparing notes later, Alice and Bob find that the particles have coordinated behaviors, which is completely inexplicable by any normal conception of space and time. How did the particles remain connected? Let's look at the experiment again. It seems as if the particles both remained a unified whole and reached both Alice and Bob. Finally, after Alice and Bob interact with the particles, they become independent. However, this is a cartoon only. We lack a proper space-time description. Alfred Nobel's Prize in 2022 did not solve Albert Einstein's problem. Spooky action at a distance, EPR, Bell nonlocality, remains an unsolved conflict between the entangled sense of wholeness and the locality, the sense of place. To recap, quantum entanglement and non-locality is very well established. There is huge experimental support for this, including a Nobel Prize. However, in opposition, there is also huge evidence supporting the 4D fabric of spacetime. Many correct predictions have been made. These successes include general relativity, which also includes gravitational waves, which seem to confirm that spacetime is indeed a vibrating four-dimensional fabric. The spacetime fabric received its own Nobel Prize in 2017 for the detection of gravitational waves from colliding black holes. So, both of these areas are very well established, but remain in conflict. There is a clear conflict. Relativity supports the space-time fabric and locality. Quantum supports spooky, non-local entanglement. We cannot simply break either of these Nobel-level theories. They're too successful, too well experimentally proven. What is the way forward? Okay, we're now up to date. Let's look at the present-day situation. This year, many conferences celebrated 100 years of quantum mechanics. Unfortunately, however, the debates continued. Also this year, the largest ever opinion survey of quantum physicists was carried out by the journal Nature. They found a great diversity of opinion. A key question that was asked was, is action at a distance real? That is, does measuring the properties of one particle instantaneously, faster than the speed of light, influence its entangled partner such that it affects the result of future measurements? The results were all over the map. About a third said yes, a third said no, spread over 4 different no options. The final third had different ideas, were unsure, or didn't reply at all. These results are strong evidence that the spooky action question remains very much open in 2025. Final thoughts on the survey. The stark disagreements show that spooky action remains unresolved even by the most complex theories such as QFT and string theory. Secondly, we lack the framework to even ask the right questions. And finally, although quantum theory and experiment agree, we remain mystified. I argue our understanding of space-time is at fault. Part 3. Critique and proposal on space-time foundations. Okay, let's take a look at space-time foundations. I define this as a physical understanding of special relativity, which is also called ontology. The values in this table are made up, but give some idea of the relative amounts of research in these areas. In particular, physics research is minimal. I have published in this area. Philosophical research is more active than the physics research for space-time foundations, but other areas which are more active, such as quantum gravity, quantum information. So why is there so little space-time foundations research? The main reason is, I think, that special relativity is a simple textbook physics and it's assumed to be complete. There is also a pseudoscience problem where a lot of crank theories are proposed in this area, which muddies the waters, unfortunately. Quantum gravity is the holy grail of physics, but unfortunately so far has failed. In around the 1940s, quantum atoms were combined with special relativity to yield quantum field theory, QFT, and this was a huge success. Then the next step to combine QFT with general relativity to produce quantum gravity failed. So part of that includes string theory, which is explained in the sidebar. So my diagnosis of why QFT has failed to produce quantum gravity is that it understands E equals mc squared, but doesn't understand spacetime, and it still does not explain spooky action. So my remedy for that is to say that we need to reinterpret special relativity, and then we could combine quantum theory of atoms with new theory of space-time to get quantum space-time, which is what I'm working on. This would then solve spooky action and provide the prerequisite for quantum gravity. So we'll look at this more next. How do you invent a theory of gravity? Historically, a new theory of gravity has been found by combining ideas of space and time with ideas of gravity. So Newton definitely already had ideas about space. He knew about planets and the sun and the moon and so on. So he knew about space before he invented his theory of gravity. In a similar way, Einstein combined his new ideas of space-time with Newton's gravity to invent his theory, general relativity. So in both cases, a space-time theory was added to a gravity, ideas about gravity, to get the new theory of gravity. However, this strategy was then abandoned and was not applied to quantum gravity. So let's take a look at that. In 1915, Einstein combined his space-time theory with Newton's gravity to create a new theory of gravity. Unfortunately, this strategy of combining space-time with gravity was then abandoned and progress stalled. The problem is that QFT does not understand space-time. My proposal is that we need to combine quantum space-time together with Einstein's gravity to generate a theory of quantum gravity. And to get quantum space-time, we need to build upon the foundations of quantum foundations and space-time foundations. We should take the interpretation of special relativity very seriously because space-time foundations can both provide a solution for spooky action and also a prerequisite for quantum gravity. In future videos, I will describe my work on quantum spacetime. In my book, A Universe of Spaces, I explain how quantum spacetime emerges from the spooky action hidden within Einstein's special relativity. Okay, that's it. Thanks for listening. For a deeper dive, check out any of the links on screen.